Assalamu alaikum everyone, this is Engineer Ahmed and today we're going to talk about the material science. So, what is material science and why should we know about it? Well, the materials drive our society through the Stone Age, Bronze Age, Iron Age, and now the Silicon Age, Polymer Age, and others. Now, as we know that with the age or certain illness, joints deteriorates, and in particularly those with the large loads, such as the hips. And as you can see in those X-rays, that in that particular area, where you can see the deterioration that could happen after time, and that could comes with the age as one of the contributing factors. So moving further, now as we can see that this is the spine, the pelvis, and the head at this part, which is, as we can see, the acetabulum, which mostly getting this part is getting mostly damages and injuries with the age. And then we've got the femur. So what are the requirements for the hip implant? Usually the requirements are such as the mechanical strength through many cycles, good lubricity, and biocompatibility. Now, moving further, and we talk about the pelvis in here. As you can see, the ball, this particular area where we have the ball and the acetabular cup, as well the fixation agent in here, the femoral stem, the femur, and the fixation agent as well in that particular area. And this is the part which implanted within our bodies once we get some sort of a surgery to fix that particular area. This is just to give you more insights of the hip implant. As I mentioned, that this is the ball and the acetabular cup and linear, and then we've got the femoral stem. So this is the entire part that will be implanted within our hip. So of course there would be some key problems and issues that we need to look at to overcome. So that would be the fixation agent to hold the acetabular cup. Then the cup lubrication material, which is quite important. The femoral stem fixing agent through the or by the glue. And we must avoid any debris in the cup, so that could provide us more smoothness between these three areas. Now we are going to talk about the develop new types of the polymers. As we can see in here that we've got two types of polymers. We've got the commodity plastics, as well we've got the engineering resins. So the commodity plastics, it comes in a large volume. Usually it's below or equal to 0.5 per lb. Some examples could be the polyethylene, polypropylene, and polystyrene. Now moving to the next one, which is the engineering resins, it comes in a smaller quantity and in between or less than $1 per lb. Some examples could be polycarbonate, nylon, and polysulfone. Now we are moving to the structure processing and properties. So as you can see here, the properties depends on the structure, hardness versus the structure of the steel. And that's an example of the steel. That means processing can change structure. So the more cooling the more we apply cooling to the steel, the hardness will increase. Now, moving to the material selection process, as we can see here, that the first is to pick the application, moving to the determine required properties, and we've got a couple of properties in here, which is the mechanical, electrical, thermal, magnetic, optical, and deteriorative. And later on this video, we're gonna talk more in depth on these properties. Now, coming to the next step, which is the properties, and then moving to the identify candidate materials. And we've got a few materials, for example, structure and composition. Now, moving from the material to the next stage, where the identify required processing. So in the processing, we can see that the changes structure and overall shape. Some of the examples are through the casting, the sintering, vapor deposition, doping, forming, joining, and annealing. Electrical. Now, the electrical resistivity of the copper. This is an example where we can see that the copper, the more as you add impurity atoms to the copper, it will increase resistivity. Moving to the thermal. So as you can see in here, that the space shuttle tiles, silica fiber insulations, usually offers low heat conduction. Moving to the next one, which is the thermal conductivity of copper. It usually decreases when we add zinc to it. So the more we add zinc to it, it will increase the, it will decrease the thermal conductivity. The magnetic storage, recording medium and magnetized by recording head, as we can see in here, and this is an illustration of that process, whereas as we can see in here, the magnetic permeability versus the composition. By adding 3 atoms, percentage of Si, makes the Fe a better recording medium. So as you can see in here, that if we add to the iron 3% of the silicon, that will improve the overall magnetization percentage. Moving to the optical, as you can see here is the transmittance, and the aluminum oxide may transparent, or maybe transparent, translucent, or opaque, depending on the material structure. And as we can see that if it's a single crystal, it will be more of visible or transparent. Moving to the next one, where polycrystals, low porosity, and you can see that it's slightly more darker or opaque, that you cannot see through. And then if it's a high porosity, it's totally blank and we cannot see through. Now, as we can see that there are certain or some cracks in here that goes in that piece of metal. So the stress and salt water usually cracks the metals and deteriorate it over time. And but by the heat treatment, it can be slowed down the cracks speed in the salt water. So this is one of the way that we can treat the metals through the heat processing. Now coming to the next part, which is the types of materials, and these are the most common materials. As we can see that the metals, we have the polymers and plastics and the ceramics. Metals is usually strong and ductile, high thermal and electrical conductivity, of course, and then it's also opaque and reflective. Whereas the polymers and plastics, it's covalent bonding, and it shares of electrons. Also, it's soft ductile, low strength and low density. Thermal and electrical insulators, and optically translucent and transparent. Moving to the last one, which is the ceramic, where it's an ionic bond refractory and compounds of metallic and non-metallic elements such as the oxides, carbide, nitrides, and sulfides. It's usually brittle, glassy, and elastic, and as well non-conducting insulators. Now moving to the next part, which is the processing, and then moving to the structure, properties, and the performance, which we're going to talk about in the next page. Now coming to this part, as you can see that the winner between all in terms of the density is the metal. Coming in the second position is the ceramics, and then polymers and the composite are almost equivalent, or like equal. Then moving to the stiffness and or elasticity of the materials, as we can see, the winner in here between or amongst the four types of materials are the ceramics, and the second will come the metals, third will be the composite, and then the polymers. Now depend on the strength of the material, where we can see that the king of the strength is the metal, and in the second position will comes the composite, and then the ceramics, and the last are the polymers. Now again, as we can see that the resistance to fracture, again the biggest winner in here is the metal, the second comes the composite, and the third one are the ceramics, and the last is the polymers. Again, as we can see that the metals comes right on the top as the winner once again for the electrical conductivity. So we can see that the metal is on the top, then the semiconductors, and the ceramics and polymers are equalized in that in terms of the electrical conductivity. And we came to an end to the summary in here, and just to very quick brief on the course goals, which is the use of the right material for the job, understand the relation between properties, structure, and the processing, and recognize new design opportunities offered by the material selection. Thanks for watching, and we'll see you next time.